Okay, here's part 2 of today's lecture on Young's experiment. It specifically references the one example problem that we'll take a look at. Please go ahead and copy down that problem into your notes. Let's go ahead and go through the solution. Basically, the problem is essentially demonstrating to us why the pattern looks the way it does, why it's symmetrical. As you'll find, the bright fringes are evenly spaced and the dark fringes are evenly spaced. That's what you saw in the demonstration of the video of the demonstration itself. Okay, so let me go ahead and read the problem here. Okay, a laser with a wavelength of 633 nanometers. That's what I'm using in the demonstration, by the way. The wavelength of visible light, it turns out, is extremely small. 1 nanometer is 1 billionth of a meter. So the wavelength lambda of the visible light that I'm using, the red light, is 633 nanometers. This is equal to 633 times 10 to the minus 9 meters. Okay, and then that light is incident upon a double slit arrangement with a slit separation of just 0.5 millimeter. That's approximately what I was using in the demonstration itself. So D is 0.5 millimeter. I'm going to go ahead and convert this into meters. This is 0.5 times 10 to the minus 3 meters. So notice that as I proceed here, everything has to be in terms of the correct units, metric SI units. All the distances here have to be written in terms of meters. Okay, and then the screen, the distance from the car that I was using in the back of the room on the ring stand to the whiteboard here, that's given to us as 7 meters. That's approximately what I was using. So all these numbers that I have here in the situation, they correspond pretty closely to what I'm actually using in the experiment. Okay, part A says, how far apart are the bright fringes? So here's basically what we're asked to find. Okay, let's say right here is the arrangement itself of the 2 slits. Right here is the screen where the pattern itself then forms. Okay, here's the distance L, here's the distance D. Okay, and then we have the interference pattern. Okay, right here is the central maximum. Here's the next order bright fringe, like so. Here's the next order bright fringe beyond that, and so on. Here's what we're asked to find, the distance from one fringe to the next. So in order to come up with that distance, let me describe it in the following manner. Let's say that this right here is the nth fringe, and its distance then away from the central maximum, I'm going to refer to as y sub n. Okay, this right here is the next order fringe, so then therefore if this one was n, let's refer to this one here as n plus 1. And then this distance that this is from the central maximum, we're going to write as y sub n plus 1. What we're asked to find in part A of the problem is the difference between the two. This is usually referred to as delta y, like so. So using the bright fringe equation, what I have to do is take each of the expressions that I'm about to write down, write them in terms of y, and then just subtract them from each other. So here's the process of doing that. All right, so first of all, recall that the bright fringe expression from part 1 of today's lecture is the following. Think of this right here as specifically for the nth fringe. And then therefore, I'm going to go ahead now and rewrite the expression, but now specifically for the n plus 1 fringe. That is like so. So notice the notation that I'm using here when I write down the expression for the 2 fringes in this manner. And now what I'm going to do is just take each of these expressions here. I'm going to go ahead and just subtract them from each other. I'm going to take this expression here minus this expression, and then I'll solve for what I'm referring to as delta y. All right, so let me take this expression here, subtract from it the other expression, like so, and then watch what begins to happen here on the right-hand side of the expression. On the right-hand side, I end up with n lambda minus n lambda, which drops out, and then 1 times lambda is left over. Over here, on the left-hand side of the expression, the d and the l is common to both terms, so I could factor it out. And then I have y sub n plus 1 minus y sub n, which is the delta y that I wrote on the board earlier, like so. And now we just go ahead and solve for delta y. Notice that everything that is here is a constant. So then therefore, the spacing between the bright fringes is always the same value, this quantity here, and this is why the bright fringes appear symmetrically. All right, so let me go ahead and calculate this out. As I said earlier, everything has to be in the correct units, as I've written on the top board. So I first of all have y, which is 7 meters. Multiply that by the wavelength, 633 times 10 to the minus 9, and then divide that by d. 0.5 times 10 to the minus 3. And then therefore the separation between the fringes here in terms of meters is about 0.009 or so. Meters like so, which is 9 millimeters. It's about a centimeter. So when we saw the pattern in the demonstration, ultimately then the fringes were about 1 centimeter apart. Okay, now in part B of the problem, now we're going to do the same calculation for the dark fringes. So let me go ahead and do some erasing here. Okay, go ahead and pause if you need to in the video to recopy here this diagram, because now I'm going to redraw on this diagram what happens for the dark fringes. All right, so the dark fringes are basically, for example, here and here in between the bright fringes on either side of the central maximum. And then like I did in part A of the problem, let's think of this right here as the nth dark fringe, and then therefore this distance here is y sub n. This here is then therefore the n plus 1 dark fringe, and then therefore this distance here is y sub n plus 1. Once again, what we're going to calculate here is the spacing between the dark fringes, one value minus the other. Now, here on the bottom board, I'm going to go ahead and rewrite my dark fringe expression now. So first of all, in terms of the nth fringe, the right-hand side of this equation will be the following. There's the odd multiplier. But now I also have to write this for the n plus 1 fringe. So right here, write this now as n plus 1. Okay, let me give myself some room here. That then looks like this. Like so. So notice what I did here. I replaced this n with its n plus 1, the next fringe over. If you simplify these large brackets here, you'll notice that you get a 2n plus 3. Like so. So take a look at that carefully. And then what I'll do, like I did in part A, is I'll just take one expression and then subtract from it the other. So let's take this expression minus this expression. Like so. So take a look at that carefully. Once again, this is the n plus 1 fringe. Here's the right-hand side of that equation. Here's the nth fringe. Here's the right-hand side of that equation. Once again, taking this minus that. Okay, let me do some erasing here. Like so. And now let's go ahead and simplify the right-hand side of the expression. So I have here 2n lambda over 2 minus 2n lambda over 2, which drops out completely. And now I'll do this in 2 steps with what is left over. Right here is a 3 lambda over 2 minus then a 1 times lambda over 2. Like so. And then if you do the math there on the right-hand side of the expression, this right here is just the wavelength lambda. Over on the left-hand side, it's the exact same thing as it was before. Factor out the d over L, and then you have y sub n plus 1 minus y sub n, which is the delta y. So, and then we solve for delta y. That then gives us this. This is the exact same expression as it was earlier for the bright fringes. So once again, the distance between the dark fringes is 0.009 meters. That's 9 millimeters. That's about 1 centimeter. So the spacing between the bright fringes is exactly the same as the spacing between the dark fringes. This is why the pattern looks the way it does, why it looks completely symmetrical on either side of the central maximum. Okay, and then briefly, there's a part C here to the problem. This just illustrates in part C that all of the angles that are in play here in Young's experiment, as I said at the outset, are extremely tiny. So here's what's asked for in part C. So it says, what is the angle made by the first bright fringe beyond the central maximum? So on either side of the central maximum. Let me just go ahead and redraw the diagram here for part C of the problem. Okay, once again, you may want to redraw this diagram here for part C, just so your notes don't get too cluttered up with the same diagram. Let me neaten it up a little bit like so. Okay, and then here's what we're asked to find. Here's the central maximum, here's the first bright fringe beyond it. Okay, first of all, this distance here. This is our delta y from before of 0.009 meters. And then specifically right here is the angle that we're asked to find on this diagram. This is specifically for the n equals 1 bright fringe. So just a little bit of tangent. So tangent of theta is equal to the distance delta y that we found earlier divided by L. The angle here is going to be extremely tiny. I'm going to go ahead and make sure that my calculator is in degree mode in order to find it. So just the inverse tangent of 0.009 and then divided by 7 meters. The angle here is less than 1/10 of a degree. The angle, it turns out, is 0.07 degrees like so. So making the small angle approximation, as I did earlier in the original derivation of our expressions for Young's experiment, is perfectly valid to do. Okay, that concludes today's lectures. Today's shirt was obituary. Stay safe, crush the curve.